Good afternoon, everyone. It's my great about multi-dimensional indoor location information model. And first of all, I'd like to introduce the content of my presentation. And from the screen, there are 5 parts to explain my work on indoor location model. And the introduction includes background and related work about my work. So the requirements part will introduce the reason of developing the indoor location model. Then I will explain indoor location model in detail. After this, there's a simple indoor location test based on this model. Finally, I will make a short conclusion and introduce the future work based on this model. Okay, the increasing demand of indoor and outdoor seamless navigation and local surface need a useful navigation model, which should both adapt to the outdoor and indoor environment. To a certain extent, as outdoor navigation is very well developed, here we just focus on the indoor environment. The navigation's basic element is location, and with help from the project of the Chinese standard of multi-dimensional indoor location information markup language. And here we just call it as indoor location ML in briefly. I'm not very sure this calling is whether very suitable, and I will appreciate if anyone has a better name to call it. We define the ontology of indoor location information based on the city GML and indoor GML, and provides a GML-based format for the indoor routing and the navigation of different routes. And the indoor location model is the core of this markup language. As shown in the figure below at the screen, we draw a simple function frame to introduce the developing way of our indoor location ML. Okay, as shown in this table, I'd like to introduce a brief collection about the standards related to the indoor navigation or location information. As well known to everyone, the CTGML is established by OGC, and it includes common definition of the basic entities, attributes, and the relations of a 3D city model. And based on the LV4 model of CTGML, the indoor GML, which also established by OGC, is to establish a common schedule framework for indoor navigation application. These 2 standards are most important reference about indoor location ML. And the ISO 19148 is the 9-year reference system standard, and the ISO PT 19141 is a standard about location. And the 3 ISO standards are all about the navigation surface is on location. And the ISO TC 204 and IEEE RAS are the expanding standard for conforming to the requirements of indoor service. Also, the indoor service has been attracted the large enterprises' attention. About 20 enterprises such as Nokia, Sony, and Samsung are organizing the Global Indoor Location Union. Okay, from the screen we can see the traditional outdoor map is very difficult to meet the needs of indoor activities such as shopping, like the front speakers says, and some route navigation. And 80% to 90% of the time human are in the indoor, and 80% of the human data connection are from the indoor. And based on these elements, we'd like to introduce the indoor navigation based on the indoor location model. And based on the elements of the related work and go with the indoor location ML, I'd like to introduce the requirements from the 2 aspects. Firstly, is the theoretical requirements. The traditional location-based surface is still it's like the traditional 2D map with contextual noise. As shown in the picture, this is the Google Map, Google Maps in Indo map, and the red circle and the arrow is full with contextual noise, and this is the second floor of this shopping mall, and it's very confused. And also, if the traditional map needs to contain good semantic information, it may be too complex to read for users, and the 3D scene could remember this situation naturally, as the 3D model can express the real indoor environment. Even the map reader knows nothing about the map. He or she could distinguish what is a room, what is a staircase, what is an elevator. With the process of creating an indoor navigation map, we could also provide a semantic navigation route with the help of indoor location model. And the user may like this kind of navigation naturally. And aiming at the user's indoor location and surface requirements, which means that users may not care about the indoor location model, but do care about the questions like this. And where I am, is there a way I could go to the supermarket at the airport to answer users' questions? Indoor data producer and the indoor service provider is the indoor location model. Knowing how to specify location, just like the location model present here, and the 3D modeling, 3D building model, and for example, the LOD4 building model of CDJML, and the model representation, the sensors, it's possible to identify the location of users in the indoor environment. As shown in the screen, in order to meet requirements of large variety of applications, the indoor application use 3D spaces of the building, and the indoor location and the user analysis methods provided by indoor service provider as a telecommunication company. And the 3D space of the building are defined as a room, corridor, window, doorway, staircase, elevator, and something like that. The user analysis methods for active pushing location service of interest to the users. For example, either indoor navigation apps on smartphone or desktop application. In the future, users can be navigated or they can be provided with different services in a similar manners and outdoors. In case of business-oriented applications such as shopping or airport or hospitals, more complex spatial, mental, and location service can be provided. Yet, another case can be distinguished for building managers who need even more information about the structure of the building, furniture, and something like that. And the indoor locations representation is based on absolute location and relative location, based on the two aspects of qualitative and quantitative. Absolute location should be a point or an abstract region that is measured with respect to the origin of the standard coordinate system in geographic space or in context. And the relative location should be a position that is measured or described with respect to another location, not the origin of the coordinate system. And based on the principle of description of indoor location, we have designed the detailed information of how to describe a dynamic indoor location from the UML class diagram of indoor location model. Indoor location is an abstract class. The root is the root of the indoor location model. As required by real-time navigation, all location in the indoor environment is to be assigned to a property of life cycle. And so the class of life cycle based on the TM reference system, which is introduced in ISO 19108, is also associated with indoor location. Based on indoor location, there are two general ways to define indoor location in details: indoor absolute location and indoor relative location. The indoor absolute location allows to define point or cell in geographic space that is measured with respect to the origin of the standard coordinate system. And there are geometric absolute location and semantic absolute location, arranged by the indoor absolute location. The geometric absolute location contains the description of the cell location and range of spatial cell location. The spatial reference system, typical Cartesian coordinate system, and the geometrical coordinate. The range of spatial cell location is defined by start location and end location, which were defined by spatial cell location, and it contains some the index of octree and the spatial granularity. The semantic absolute location defines location by address and attribute of a location, including the information of a floor owner and the description. For example, a description indoor absolute location as a coordinate like 100, 110, containing the feasible geometrical XYZ coordinates to define a location and the invisible information of a system parameters of a coordinate system. Similarly, a description as A, B, C, and 1 containing the feasible index, which is the ABC and of octree and the invisible parameters of trees. And the indoor related location is more complicated than the indoor absolute location. It distinguishes between geometrical relative location and semantic relative location. The geometrical relative location contains a list of geometrical reference location, and which defines the reference object and the referenced object, which are realized by the geometrical reference object with information of our geometrical absolute location and the description. The value of distance, which defines the unit and value of a distance. And the semantic relative location include a list of semantic reference location. The location of semantic reference is arranged by the semantic reference object, which is realized by the semantic absolute location with information of a semantic absolute location and the description. The relation of distance, which includes the value of distance and the distance description. The relation of the direction, which includes the value of direction and the direction description. The relation of topology, which defines adjoint, inside, and intersection and link. The relation of indoor location, which defines down, left, right, and up, with a third reference object. And comparing with the definition of indoor location model, we also have a hierarchic structure to define the semantic information of the example building. Indoor space is divided into 4 parts: the portal, container, surface, and obstacle. The portal could be an OI portal, which means that connect outdoor environment and the indoor environment, such as exit or entrance or window. And for example, and all the portals have connected status locked means the portal cannot be used or passed, and unlocked means the portal could be used or passed. And also the counters is the main complement of a building. It contains rooms, passage, and floor. The floor is composed by room and passage. And the passage could be a corridor or connector. The connector should be a connector that connects outdoor environment and indoor environment, such as the escape leader is a time continuous connector, and another connector, the connector between indoor spaces, such as stairs and elevators. And the surface is just the floor, and the furniture is obstacle. In this experiment building, we do not create darker paths, and the example is based on the limited paths, like a window, door, staircase, room, corridor, and the floor. The up table ensures the location information of this building, and the down table ensures relation of topology of indoor location. The symbol the checking symbol means the relation between the location is at the joint, and the symbol the cross symbol means disjoint. And this is the step of the indoor verification test. First of all, we create a LD4 building model, and we use some methods to get the indoor space like every room and a staircase. For the explaining, I just get the city gem and the indoor gem picture, and then based on the indoor space, we create a SEER army to get the indoor rooms surface project on the XY plane, and then we basically on the date of this we get the topology relationship of the region. Then we combine all the region and cleave the staircase, and then based on this date we create a verification mesh date for verification. And this is a picture of the indoor verification test. And from this picture, we will see there's a root line from here to here, and we also can see from the three pictures the collection of the verification mesh also can be computed, and also from this, because of the door is closed, so the verification root is break, and based on computing of the verification mesh. And here's the conclusion. And indoor model location has a potential capacity to describe geometric location and semantic location of indoor environments, and the different users groups and the information needed for these different tasks. And based on this indoor location model, we'd like to improve the multi-dimensional indoor location information standard of China, and we will improve the example for the dynamic environment indoor verification, such like a fire and a multi-layered building, and based on the dynamic environment in the building, and we can compute the root dynamic in real time. And here is the example. We also like to do the indoor routing example and the indoor emergency example based on the indoor location model. Okay, that's all. Thank you.